we've seen from our discussion of facies analysis in the last module that it is of the utmost importance for a geologist to understand both the general and the detailed nature of the formation he's investigating. Such understanding comes from good interpretation and a lot of quality thinking.
We should remember, too, that identifying the sedimentary environment in which a prospective formation originated is not the end point, but rather the beginning to truly successful exploration, and for that matter, efficient production as well.
Now, in this module, we'll be looking in detail at non-marine environments. Essentially, we are starting at the first major settings of sandstone deposition from the sediment source area. In successive modules, we'll be approaching shoreline, transitional marine environments, and then moving into deeper and deeper water regimes.
Before we begin our look at non-marine sandstones, let's briefly review the three main information avenues a geologist normally follows in facies analysis.
These include examining, 1, the overall picture, that is, tectonic setting, basin architecture, and the like. 2, direct evidence, meaning such things as core samples, outcrops, thin sections, in other words, the rocks themselves. And 3, indirect evidence, such as seismic data and wireline logs, that is, data we have generated through instrumentation. All these need to be examined at some point in facies analysis. Ideas need to be found, tried out, discarded, replaced, and hopefully, over time, confirmed. Good interpretation is therefore a complex evolutionary merging process, not a simple linear improvement in understanding over time. It requires knowledge, experience, humility, and again, imagination. Training such as that given here can only provide the first of these, the knowledge. The rest depends completely on the individual scientist.
Now, with this fresh in our minds, let's remain onshore and look in detail at the major non-marine environments of importance to petroleum geology.
When you're exploring for petroleum, non-marine sandstones are traditionally much lower on the priority scale than their marine and transitional marine counterparts. Most oil, after all, originates from marine source rocks. Unfortunately, this bias has often caused potential traps in non-marine sediments to be neglected. But now we know that non-marine sandstone facies can be important in their own right, and exploration directed toward these reservoirs can be very rewarding.
Of the 5 major non-marine environments, 4 produce sandstone facies, which collectively have yielded huge amounts of petroleum. These are the braided stream environment, the meandering stream environment, the dune sands of the aeolian environment, and the sandstones found in lake environments. For each of these environments, we'll first look briefly at the physical processes most responsible for deposition. We'll also examine how each facies evolves, both in space and time. Then we'll go to the rocks themselves and investigate what we've seen to be the 5 cornerstone parameters of all facies analysis: lithology, paleontology, sedimentary structures, associated environments, and geometry. By considering both direct and indirect species of evidence, we'll be able to come up with a few general prescriptions that will help identify each environment in the subsurface.
This, of course, is the central aim of the explorationist, but, as we've seen, it's not the final one. We'll also be looking at some specific reservoir characteristics and at some examples of important fields which produce from non-marine rocks.
A meandering stream, a lake, a dune field, a braided stream. These are the major environments in which non-marine reservoir sands are deposited. The areas they cover are small, usually insignificant when compared to the large continental regions that are non-depositional, undergoing erosion or in equilibrium, where neither erosion nor deposition are taking place. Most continental environments, therefore, are not important to petroleum geology, except for the unconformities and migration paths they can produce.
But the 5 depositional settings which we'll be looking at are important to exploration, since they sometimes contain oil and gas, large amounts of it. Let's begin by briefly looking at braided streams near their upland source, on the alluvial fan. This environment is basically the result of a sudden change in setting. Most often, a fan develops where a stream leaves an upland area and spreads its heavier debris out over more open terrain, creating a cone that builds over time. A large part of the sediment deposited in the fan environment is by debris flows and landsliding, which add coarse, often chaotic, conglomeratic debris, which is commonly called fanglomerate in the rock record. This debris is usually cut by a network of shallow, vein-like channels filled with coarse, cross-bedded sands. And during times of flooding, much of the fan receives a thin, sheet-like cover of finer-grained sand and silt.
In general, then, fan material is poorly sorted and of unpredictable porosity and permeability. As a result, alluvial fans have proved to be only of minor importance as petroleum reservoirs.
Because of this, we'll reserve our detailed discussion of this environment for the manual. We should realize, though, that alluvial fan sediments are very important to diagnosing the subsurface because, by themselves, they often indicate both tectonic setting and a possible range of associated environments that could have produced good reservoir rocks.
Let's take a detailed look at one of these associated facies, one which has served as the reservoir for several well-known giant fields. As we move a bit further from the mountain front, that is, from the sediment source area down off the alluvial fan, we find ourselves on the plain of a braided stream or river. Braided channel sands, as we've just seen, are found on alluvial fans, but can in fact form in any situation where rivers are overloaded with sediment. This means they are usually found relatively close to a sediment source, where detritus is apt to be abundant, immature, angular, and coarse-grained, while slopes are relatively steep or moderate, and the water discharge is often seasonal. Braided streams, then, often occur where there's little vegetation to hinder runoff and erosion. Today, this restricts them to arid or glacial environments for the most part. The high sediment supply means that during times of normal discharge, braided streams have low erosive power. Most of their energy is used just to move bedload. They therefore cut broad, low-banked, and flat-bottomed channels. These become rapidly choked by their own detritus and are forced to divert laterally. The most characteristic features of braided streams are these channels and their sandy cross-stratified mid-channel bars.
What we see here is a time-lapse photographic sequence showing the actual switching of channels and channel bars in a braided glacial outwash stream. Here, over 3 hours of continual stream action is compressed into only a few seconds. Though the mid-channel bars are usually emergent, they form only during periods of high discharge. Increased currents erode sand from the upstream end, as well as from the stream bed and banks, and add some of this to the downstream end and sides of the bar. Consequently, most of the individual bars and channels are unstable, varying in shape and position with each new flood stage. Channels are continually abandoned, recut, and filled. In semi-arid or temperate regions, if a veneer of fine-grained sediment is deposited on a bar, a plant cover may form during a low water stage and effectively stabilize the bar against further erosion. Sediment accretion may also occur when an active channel becomes abandoned. These channels are usually floored by a thin coating of pebbly lag deposits. They then become filled with the silts and clays normally transported through the active channel system, which will settle out of suspension in these backwater areas. Such relatively straight shale-filled channels, usually only a meter or so thick, are occasional but characteristic features in most braided sandstone formations.
If we look for a moment at a typical vertical sequence in this facies, we notice that 3 lithologies, channel pebble lag deposits, cross-bedded bar sands, and abandoned channel silts and muds, form the major subfacies that will be seen in cores. But it is the active channel sequence which dominates the record of a braided stream. If preserved as a whole, each channel sequence shows a sharp erosional base covered with a thin pebble lag, overlain by trough cross-stratified sands, and some tabular cross-bedding, topped by rippled sand, and sometimes overlain by muds that cap a stabilized bar. This is usually accompanied by an upward fining change in grain size, though sudden flooding may sometimes create the reverse pattern. The thickness of each active channel sequence will be usually in the range of a few meters, less than water depth during flood stages.
The coarse, often pebbly bedload sandstone that fills the active channel generally makes up as much as 90% of an entire braided stream section. These channel sequences are commonly stacked, each on top of the next, to form continuous sandstone or conglomerate intervals that can be several hundred meters or more thick. It is this facies which interests the petroleum geologist, for it often has excellent reservoir properties. The sandstones have little clay matrix and are therefore clean with a high primary porosity. They usually contain very little, if any, organic matter. The changing water levels within braided streams and the continually shifting channels and bars create a hostile environment for most plant and animal life. Moreover, floods often wash away any organic debris which does accumulate. Consequently, in the sedimentary record, this facies rarely contains fossil remains. Relative closeness to the sediment source area means that the sands in braided streams are often immature, with quartz and feldspar grains being rather angular. Also, because these sands are deposited above the local water table, they frequently become oxidized and take on a red or yellowish iron staining.
The paleocurrent patterns produced by the sedimentary structures of this facies are often nicely shown on dip meter logs. Let's look again at the braided stream sequence, and at the same time, the dip meter tadpole motifs that it generates. The shale beds, which were originally horizontal, show the structural dip, in this case a few degrees to the southeast. Such uniform dip patterns, you'll recall, are sometimes called the green motif. Cross-bedded layers, meanwhile, usually have dips of uniform magnitude and direction within each single channel sequence. On the other hand, frequent changes in both the dip direction and amount between channel sequences are characteristic.
Individual braided channels are fairly straight and deviate very little from the direction of the main channel body. Channel bars, meanwhile, build only in a downstream direction. Consequently, most azimuth changes between crossbed sets remain within a 90-degree arc, whose bisecting radius indicates the downstream direction and elongated trend of the sand body as well. Now let's look at a gamma-ray SP log of the same ideal section. Individual channel sequences that are fairly complete may produce a crude, fining upward log pattern. This, you remember, is called the bell profile and is generally characteristic of channels in many environments. As a whole, the bell pattern reflects the gradual increase of finer material in the upper part of a sequence as the channel axis migrates away. For braided alluvial deposits, however, incomplete sandstone sequences are far more common, and this tends to produce the monotonous, serrated, blocky profile seen here.
In terms of its expression on seismic sections, a braided stream does not leave a particularly unique identifiable signature. This seismic section of the braided alluvial reservoir at Prudhoe Bay, Alaska, shows the typical geometry of a large sand body. The basic morphology is essentially thin and sheet-like. The internal homogeneous lithology of braided stream deposits often lacks continuous velocity contrast, and this means that there should be few continuous strong reflectors.
Actually, braided alluvial deposits are one of the easiest non-marine facies to recognize in the subsurface. Let's pause for a second and summarize the diagnostic features.
Cores reveal thick sections that are almost entirely made up of non-fossiliferous cross-bedded sands with gravel layers. Dip meter readings show uniform paleocurrent trends within a single active channel, with changes in dip direction between two or more channels. This gives rise to a monotonous, blocky response on wireline log curves, which are neither as smooth as those of clean, well-sorted windblown or beach sands, nor as shaly as those of meandering channel floodplain deposits.
Overall, then, since braided stream sands occur as thick, laterally extensive sheets with high initial porosities, And since the rare, thin shale bodies cannot restrict fluid migration, their potential reservoir quality is excellent, far superior in general to the sands of meandering streams, which we'll look at a little later on in Unit 2. We might assume that because braided streams most frequently occur in continental regions, far from potential marine source rocks, they should usually be inaccessible to petroleum accumulation. At the same time, many of the world's giant fields produce partially from braided sands. Prudhoe Bay in North Alaska, Hassi Messaoud, and Sarir and Messala fields in North Africa, and Strat Fjord in the North Sea. In each of these cases, it was the onlapping marine shales which provided both the seal and often the source that turned these rocks into reservoirs. Let's look at two examples, the first of which lies in North Africa.
The Messala field, discovered in 1971 near the southeast margin of Libya's oil-rich Sirte Basin, ranks among the world's largest stratigraphic traps, with some 3 billion barrels of oil in place. Prior to the discovery, seismic mapping had revealed a plunging basement nose in this region, and it was anticipated that the reservoir sandstone would wedge out against this high toward the west and northwest. This sandstone, the Sarir, is part of the braided Nubian sandstone complex that blanketed much of North Africa in the early Cretaceous, before the episode of rifting which created the Sirte Basin began. It forms the reservoir of the nearby Sarir fields, where the trap is also due partly to erosional truncation. Let's look for a moment at an east-west cross-section through the Messala field. Entrapment is due to simple unconformity wedge-out, unaffected by faulting. There are two sandstone reservoirs, separated by a red shale unit. Thick Upper Cretaceous deep-water shales deposited at the onset of basin rifting unconformably cap the upper main sand reservoir and provide both source rock and seal. The field encompasses some 130 square kilometers. Though the net reservoir sand, as shown by this isopac map, averages about 30 meters thick and is over 70 meters thick in some places, the reddish-brown sand is texturally and mineralogically immature. An SP log profile shows us the blocky appearance we would expect from braided alluvial deposits, with shale layers standing out prominently. To the east, porosity pinch-out due to a tight silica cement limits the field. Though within the field, porosity and permeability are adequate, the high reservoir quality is mainly due to secondary fracturing. But it is the thick, continuous nature of the braided sand sheet that contributes to the giant size of both Messala and nearby Sarir fields.
For our second example, we'll take a brief look at the largest field in North America. Prudhoe Bay on the north slope of Alaska has recoverable reserves of nearly 10 billion barrels of oil and 26 trillion cubic feet of gas. Oil is produced from several different reservoirs, but the most important of these by far is a braided river sandstone interval in the Permo-Triassic Age Sadler-Rochit Formation. A north-south cross-section through the field shows its principal features. A combination structural stratigraphic trap has been created by a gentle anticline cut by a number of normal faults on its northern flank. Just as at Messala Field, erosional truncation is an important feature of this braided reservoir. Like the Sarir sandstone at Messala, the Sadler-Rochit is unconformably capped by marine rocks, whose shales have acted as both source and seal. The sandstone reservoir forms a sheet up to 50 kilometers wide and ranges from 100 to 225 meters in thickness. Gross pay averages 110 meters. The braided upper Sadler-Rochit is made up of mainly upwardly fining, incomplete sandstone sequences, with only 5% to 15% shale. Logs run through the productive interval show the classic blocky profile of a braided alluvial complex. These sands cap an upward coarsening deltaic sequence reflected on this part of the SP log. In general, the reservoir quality is excellent, with porosities between 20% to 30%, and permeabilities from 300 millidarcies to as high as several darcies. The early pre-discovery seismic data was of excellent quality. It clearly showed the up-dip truncation of the Sadler-Rochit, and allowed industry scientists to accurately define the Prudhoe Bay structure. The Discovery well was drilled in 1968 and hit right in the structural crest, penetrating more than 120 meters of gas cap before encountering oil.
Both these examples, one from the desert, the other from the Arctic, were originally identified on the basis of the features we've discussed. Both fields are giants and demonstrate the tremendous reservoir potential of extensive, sheet-like, high-porosity sands of the braided stream environment.
The next alluvial setting we're going to be looking at is the meandering stream, which is the most widespread and well-studied of all stream environments. Let's turn our attention to this setting and the reservoir sands deposited within it. Slope gradients are now quite low. Sediment is finer grained, more mature, with better sorted, less angular sand grains. And the discharge of water is more perennial, less seasonal. The Mississippi River is about the most well-known mature meandering river floodplain in North America. It has been extensively studied and has provided what might be called the type example for much of our knowledge about this facies.
We might begin our discussion by noting that, unlike the braided stream model we've just seen, a meandering river has an alluvial valley cut by only a single sinuous and laterally migrating channel. Sand deposition is normally restricted to this main trough, which generally is narrower and deeper than those of braided streams. Fine silts and muds, usually carried in suspension, are deposited only during high water stages, when the stream rises in flood, then spreads out onto the overbank environment. During times of normal discharge, the flow within meandering channels is non-uniform. As an expression of this, the outer banks are eroded into previously deposited floodplain muds, while at the same time, sand is deposited in the form of point bars along the opposing inner banks, where the current is more sluggish. With time, the meander loops increase in sinuosity and slowly migrate downstream. Where points of undercutting meet along the narrow neck of a meander, the channel may be cut off and abandoned to form the classic oxbow lake. Meander loops can also shorten when water overflows the main channel into a low part of its point bar, forming what's called a chute cutoff. Both types of cutoffs form mainly during episodes of flooding.
These processes of channel migration and flooding produce a variety of subfacies, several of which are similar to those we saw in the braided stream environment. Ideally, for example, the active channel shows a veneer of basal lag deposits, made up of the coarsest debris the stream can move, often crudely layered and cross-stratified, overlain by point bar deposits, which are mostly well-sorted, medium to fine-grained cross-bedded sands. As migration proceeds, point bars build out laterally, following the erosion of the outer bank. Since their upper layers encounter increasingly weaker currents, the grain size of the sand diminishes upward in each point bar sequence. In abandoned channels, this building out of the sand-dominated point bar sequence is halted and covered by fine sediments that settle slowly from suspension in the Oxbow Lake, which is resupplied with material during periods of flooding.
The overbank environment contains two main subfacies that are active only during stream flood stages. The first of these are levee deposits, which are sediment buildups along the channel margins where floodwaters dump their coarse suspended debris. These are mostly fine sands and silts, deposited in layers that slope gently away from the stream channel. The second subfacies is the floodplain itself, which is composed of mud and silt that is settled out of the floodwaters that periodically rise out of the channel and cover the alluvial plain. Among these subfacies, the petroleum geologist is most interested in those associated with active channels, because only these have good reservoir potential. The others are useful mainly to help more precisely identify and map the environment. Here we see an excellent example of a small channel cut into floodplain silts and filled with coarser sand. Note the blockier, more massive appearance to the channel sandstone, and also its subdued color. These sediments are usually deposited close to the water table and are not oxidized enough to become reddish or yellow.
Let's look at this channel again in a little more detail. You'll remember that channel migration creates an overall upward fining progression in grain sizes. The specific sedimentary sequence left by migration is distinctive and therefore diagnostic for the meandering stream environment. In our ideal sequence, channel floor and lag deposits are succeeded by cross-bedded point bar sands, in which grain size and the size of cross-bed sets both diminish upward. These sands are overlain by muds and silts of the floodplain, which cover the once active channel, now filled by the point bar. The whole represents a fining upward sediment cycle. As with braided stream deposits, the total thickness of each cycle will be equal to the greatest water depth during flood stage. For meandering streams, this is generally in the range of 2 to 15 meters. But cycles are commonly repeated and truncated as channel meanders continually migrate, cutting into floodplain muds. In a gradually subsiding basin through which the river is perhaps flowing, these cycles can be stacked many times to form thick sand-bearing alluvial complexes that sometimes measure in the hundreds of meters.
The preservation of overbank sediments, meanwhile, depends upon how often meander loops migrate and on the overall rate of subsidence in the basin through which the river moves. A higher subsidence rate will mean a greater slope and, therefore, a straighter channel. A good rule of thumb to remember here is that, in total, this facies has roughly a 1-to-1 sand-shale ratio, which reflects an approximately equal floodplain and point bar development. Individual sections and wells will, of course, be dominated by one or the other subfacies, but the entire environment will show this generalized relationship, which tells us that when meandering stream facies contain noticeably less than 50% sandstone in a vertical section, it's likely that individual sandstone bodies are not connected. But when sands exceed 50%, the probability of channels being connected rises. In fact, the coarser and more abundant these sands get, the higher this probability. In production geology, this can be important in predicting if a sequence of reservoir sands will act as a single production unit, or if sand reservoirs will be isolated and require separate drainage.
Let's now look briefly at the wireline log curves these lithologic sequences produce. The upward fining gradational change in active channel sediment generates a corresponding bell-shaped response on SP and gamma ray logs. We should remember again, though, that this upward fining is characteristic of channels found in both marine and non-marine environments, and is only an ideal model. In contrast, abandoned channel fill generates a curve that reflects the existence of a few thin sandy beds in an otherwise fine-grained section, basically a non-distinctive silty shale pattern. Now, if incomplete active channel sandstone sequences without much shale are stacked, the profile will be more homogeneous, like the pattern generated by braided stream complexes. But even if the log data is somewhat ambiguous, as it often is, the features seen in cores and cuttings may indicate a meandering fluvial system. Besides the sedimentological evidence we have discussed, fossils are sometimes good indicators of the alluvial environment. Floodplains are heavily vegetated, so organic debris is often common.
Let's review quickly the common sedimentary structures seen in cores and the vertical order in which they normally occur. These reflect deposition on the point bar, which is the dominant sand body in most meandering regimes. Typically, channel lags overlie sharply scoured bases and are only crudely stratified. Then come parallel beds in rather coarse sands, the first deposits of the actual point bar. Then trough crossbedding in medium to fine-grained sands, with sets that become smaller upward. Next, recording the shallow depth of the upper point bar, thin parallel beds, climbing ripples, and small-scale crossbedding produced by a combination of low-energy currents and suspension settling. And finally, floodplain muds, perhaps with signs of subaerial exposure, such as mud cracks, animal tracks, and raindrop impressions.
Bedding surfaces within the sequence can be picked out with a dip meter log and can be used to indicate the trend of the channel axis, and therefore that of the sand body as a whole. It's evident, even in this idealized log, that the dip meter data is much more variable than the pattern we saw earlier in braided sands. But we should notice that there are three main motifs. Again, the shales have consistent low dips. The green motif, that reveals regional or original structural slope, usually less than 5 degrees. But in the sands, the major pattern is one of upwardly decreasing dips. The red motif. These higher dips within the sands measure the depositional slope along major accretion surfaces. The upward decline in dip amount indicates the gradual point bar filling of a channel, as shown here, with the dip direction pointing towards the channel depot center. When such widely spaced dips are computed, it isn't possible to differentiate crossbeds, those, say, several feet or less in thickness. When the correlation interval is shortened, however, individual crossbed sets may show up as the blue motif, which is characterized by an upward increase in dip amount, as shown here. The direction of these dips indicates the paleocurrent direction, but only at one particular location. That passed by the borehole.
In terms of geometry, like braided streams, present-day meander belts are usually oriented perpendicular to shorelines. They often feed into and are part of deltaic environments, for example. Individual channels, of course, because of their overall snake-like form, can show almost any direction at a particular point. They are, however, usually local in extent, while meander belts may be many hundreds of kilometers in length and 20 times wider than a single meander loop, say tens of meters to tens of kilometers. In each case, however, the sand bodies produced will be essentially linear. As we've seen, some active channel sands fill much of the meander belt, eroding the floodplain muds through channel migration. Or in another common scenario, increased slope and straighter channels produce more isolated, so-called shoestring sand bodies, less than a kilometer or so wide.
A good seismic section of a channel should show strong reflectors, marking the abrupt contact between channel wall and sandy fill, but relatively poor internal reflections. Of course, not all channels are as ideal as this one, and we need more information to interpret this as a fluvial channel. Similar channel geometry can be found in deltas, estuaries, or submarine fan environments too. And in most sections, channels can't be seen as nicely as in this example. A relatively new and sometimes very effective technique is to take a horizontal time slice of 3D seismic data. This may reveal unique geometries, in this case, a meandering channel. Acoustic velocity contrasts between the channel fill and surrounding floodplain allow this sort of resolution to occasionally add telltale clues to facies identification.
For the geologist, various subsurface mapping techniques also prove useful in delineating both the location and shape of channels and channel complexes. Detailed structure contour maps, for example, can be constructed on an unconformity surface beneath channel sands, using elevations taken from log data. If enough information exists, we can construct a map with this kind of detail. By connecting the points of greatest curvature, we see the direction of paleo-drainage. This method is useful mainly in areas without structural deformation, and more importantly, where an abundance of well data exists.
The method which most geologists use is to construct and contour isopacks from a lithologic marker to the base of the sand body itself. For an overlying datum, the geologist will use the maximum isopack thickness to reveal the probable channel axis. For an underlying datum, the isopack minimum is used, as shown here. If we can be confident that most of the valley fill is sandstone and the maximum sand trend coincides with maximum downcutting, we can map the sand isopack itself.
At this point, let's briefly review the ways to recognize meandering stream facies. We remember the major lithologies: thin channel lags, fining upward accumulations of cross-bedded point bar sands, and floodplain shale and silt that may have diagnostic microfossils. We remember also the characteristic suite of sedimentary structures, with cross-stratification in sands becoming smaller as grain size diminishes upward. At the same time, there may also be swamp coal deposits that indicate the backwater floodplain subfacies, or truncation by the next overlying sequence. Bell-shaped log curves are typical of the upward fining channel fill. In addition, there are the different dip log motifs: green for shale, red for accretion surfaces, blue for crossbeds. And overall sand geometries are generally linear and trend perpendicular to paleo shorelines, while individual channels are lens-shaped in cross-section.
Now, in terms of their reservoir attractiveness, as we've mentioned, meandering stream sands seldom form as high-quality a reservoir as those deposited by braided streams. The much higher shale content and the general preservation of sand bodies in localized shoestring and linear shapes, encased and divided by floodplain and abandoned channel shales, usually make for rather small, separated petroleum fields that produce from stratigraphic and combination traps. But it is also true that within meandering stream sand bodies there is usually fair to excellent porosity and permeability, and individual channels are sometimes stacked to form thick reservoir intervals. Surrounding shales, then, are good seals, and sometimes source rock, too.
To round out our discussion of meandering streams, we'll look briefly at two field examples from the Rocky Mountain region of western North America. During the Cretaceous, a vast interior seaway provided great quantities of organic-rich marine shales, from which oil and gas were later generated. During the Tertiary, these hydrocarbons became trapped in the fluvial facies of numerous rivers, which had flowed into the lagoons, estuaries, and deltas that rimmed the margins of this seaway. For our first example, let's look at a Cretaceous fluvial channel system mapped from well dated near Lloydminster in the Alberta-Saskatchewan border in western Canada. Looking more closely at this channel system, we see the strong dendritic pattern to these channels. When we go to a cross-section through one of these channels, we see that sands are discontinuous, with individual bodies being less than 30 meters thick. The main channel sands are draped over a Paleozoic basement high, and the actual net reservoir thickness varies a lot across this structure. Notice how straight and wide these channels appear to be, and also the direction of their branching. This tells us that the paleoslope was relatively high and to the southeast, into the Cretaceous Ocean.
For our second example, let's look at the eastern flank of the Powder River Basin in Wyoming, where the Coyote Creek field, with reserves of 20 million barrels, provides an interesting variation. Looking for a moment at the simple isopack map, we see a point bar reservoir situated adjacent to an abandoned shale-filled channel, with several low areas on the bar itself also filled in with clay and silt. In cross-section, we can see how the reservoir lies next to impervious shales, which were originally muds that filled an abandoned channel oxbow. The fine-grained sands have porosities between 15% and 24%, permeabilities of 200 to 300 millidarcies, and a maximum oil column of about 12 meters. Coyote Creek, then, represents almost ideally preserved point bar geometry.
In contrast to the large sheet-like sandstone reservoirs created by braided streams, the meandering river has throughout geologic time generated small, localized sand bodies, which are often difficult to detect and map in the subsurface. For this reason, we may infer that where most major braided stream reservoirs have probably been identified and explored, there are still an attractive number of as yet undiscovered fields in shoestring point bar sands in basins all over the world.